Welcome back to G Fun Facts Online. Today we are diving deep into one of the most exciting intersections in modern physics. We are talking about a collision between the incredibly large and the incredibly small. For over 100 years, physics has been a house divided. On one side you have Albert Einstein's general relativity. This is the physics of the massive. It is a majestic cathedral of geometry where gravity isn't a force, but the curvature of space and time itself. On the other side, you have quantum mechanics. This is the rulebook for the subatomic world, and it is chaotic, probabilistic, and follows a completely different logic. These two theories historically hate each other. If you try to combine them mathematically, the equations usually explode. But while string theorists and cosmologists have been looking to the stars or massive particle colliders to reconcile these two, a quiet revolution has occurred in a much smaller place. It is happening in the silicon and carbon landscape of a microchip. We are exploring the era of Einstein on a chip. In a groundbreaking development reported in late 2025, researchers have successfully identified a hidden geometry within quantum materials. This is a feature known as the quantum metric. It forces electrons to move exactly as if they were falling through the warped spacetime of a black hole. This is not just a simulation. Mathematically, these electrons are experiencing gravity. By bending materials instead of space, and manipulating quantum wave functions instead of planets, scientists are unlocking a new branch of technology called gravitronics. Today, we are going to explore how we learn to bend electrons like gravity, and why this breakthrough could lead to the ultimate green supercomputer. Let's start with the breakthrough itself, specifically the concept of the hidden geometry of quantum matter. This headline news comes from a collaboration involving the University of Geneva, or UNIGE, and institutes in Salerno in Italy. To understand why this is a big deal, we have to look at how we used to think about electricity. For decades, we believed that the only thing affecting an electron's path in a solid material was the electromagnetic force, essentially the electric potential of the atoms around it. However, the UNIGE team discovered something profound. They found that in certain quantum materials, the wave function of the electron possesses its own intrinsic curvature. Remember, the wave function is that mathematical cloud describing the electron's probability of being in a certain place. This intrinsic curvature is what they call the quantum metric. Here is the best way to visualize this. Think of a standard microchip as a flat sheet of paper. On this flat sheet, electrons travel in straight lines. The discovery reveals that in specific materials, this paper is crumpled and twisted on a quantum level. The electron doesn't feel a force pulling it. It simply follows the curve of the quantum metric. It curves its path just as light curves around a star. Why does this matter for engineering? It allows engineers to steer electric currents without using external magnetic fields. Magnetic fields are bulky and energy hungry. With this new physics, the gravity is built directly into the crystal lattice itself. Now let's get into the physics of how you can fake a universe inside a rock. To understand how a chip can mimic gravity, we must look at Einstein's central equation, the metric tensor, noted as g mu nu. In general relativity, this tensor tells you how to measure distances in space. If the metric is constant, space is flat. If the metric varies, perhaps due to a massive object like the sun, space is curved. In solid-state physics, we don't have planets to warp space. But we have something else. We have strain and topology. This connects directly to the Dirac equation. In normal materials, electrons are massive and sluggish. But in advanced materials like graphene and Weyl semimetals, electrons behave differently. They become massless Dirac fermions. They zoom through the lattice at 1/300th the speed of light. They behave more like photons than matter. Because they move relativistically, they obey the Dirac equation. If you deform the lattice they travel through, if you stretch it, twist it, or heat it unevenly, you change the distance between atoms. Mathematically, this change enters the Dirac equation exactly where the metric tensor enters Einstein's equations. The result is fascinating. To the electron, the distorted lattice looks identical to a gravitational field. It doesn't know it's in a lab in Geneva or Rochester. As far as the electron is concerned, it thinks it is skimming the event horizon of a black hole. So how do we actually build this? Scientists are currently using three main flavors of artificial gravity to build these gravitational chips. The first approach is strain engineering, or what I like to call the rubber universe. This is the most intuitive method. It involves physically stretching materials. Research from the University of Maryland and Berkeley lab has shown that if you take a flake of graphene, which is a single layer of carbon atoms, and stretch it into a specific triangular shape, you create a pseudo-magnetic field. The effect is staggering. The strain creates a gauge potential that mimics a magnetic field of 300 Tesla. For context, the strongest continuous magnet on Earth is only about 45 Tesla. This massive field is created just by stretching the material. The application for this is called valleytronics. This allows us to separate electrons by their valley, which is a specific quantum property. This could lead to a new type of computing that uses no charge, reducing heat dissipation to near zero. The second flavor involves Weyl semimetals and the axial gravitational anomaly. This is the most cosmic approach of the three. In 2017, a team led by IBM Research and the University of Hamburg used a crystal called niobium phosphide. This is a Weyl semimetal. They used it to observe a phenomenon previously thought to exist only in the moments after the Big Bang. It is called the axial gravitational anomaly. In flat space, certain conservation laws like charge and momentum are rigid, but in curved space, they can break. By applying a temperature gradient, essentially heat, to the Weyl semimetal, the researchers simulated a gravitational field. They observed a pumping of electrons from one quantum state to another that violated classical conservation laws. This happened exactly as string theory predicts for the early universe. The real-world use for this is immense. This Hab anomaly generates electricity from waste heat with incredible efficiency. It could revolutionize energy harvesting. The third flavor is photonic crystals. This is about bending light for 6G communication. It's not just electrons that can be manipulated this way. Researchers at Tohoku University and Osaka University have created photonic crystals with distorted lattices that act as pseudogravity for light. As we move to 6G communications, we will be using terahertz frequencies. These frequencies behave like light. We need to steer beams around obstacles without slowing them down. Instead of using lenses, which absorb energy, we can use a gravity chip. This allows us to curve the beam of data around a corner, just as a galaxy lenses the light of a distant quasar. Now, you might be asking, why go through the trouble of simulating gravity? What is the killer app for gravitronics? It is not just about winning a Nobel Prize. There are three major reasons. First, we have the end of heat through ballistic computing. Modern processors are limited by heat. Resistance occurs because electrons smash into atoms, scattering and releasing energy. In a gravitational material, electrons follow geodesics. A geodesic is the path of least resistance. They don't scatter. They flow like water down a frictionless pipe. This is called ballistic transport. University of Rochester researchers have proposed ballistic deflection transistors that steer electrons using these geometric forces. They operate at speeds unheard of in silicon, with a fraction of the heat. Second, we have quantum protection. Quantum computers are notoriously fragile. A slight vibration destroys the calculation, a process called decoherence. However, geometric properties are topological. This means they are robust. Think of it this way. You can crumple a sheet of paper, but you can't change the fact that it has four corners. By encoding quantum data in the curvature of the electron's path, we can build qubits that are immune to local noise. Third, we have laboratory cosmology. We cannot fly to a black hole to study it, but now we can build one. Researchers at Utrecht University have proposed using these chips to create an event horizon for spin waves. By creating a region where the flow of the material is faster than the speed of the waves, you create a point of no return. This allows scientists to study Hawking radiation, the heat emitted by black holes, right on a tabletop. This could answer fundamental questions about the death of the universe. In conclusion, we are witnessing a rare moment in history where abstract theory crashes into concrete engineering. The Einstein on a chip breakthrough proves that geometry is physical. We don't need to generate massive forces to control the universe. We just need to shape the stage on which the actors play. As we master the quantum metric in strain engineering, we are moving toward a future of electronics that mimic the elegance of the cosmos. These devices will be frictionless, efficient, and guided by the invisible hand of geometry. The next supercomputer won't just calculate physics, it will be physics. Thanks for listening to G Fun Facts Online.